Welcome back, everyone. We are to the part where we're going to kind of summarize up all of the ways to sketch a curve. And we have 7 steps here, and we're going to go through all 7 of them for these 2 functions here. First step is find the domain, vertical and horizontal asymptotes, x and y intercepts, critical and inflection values, and then use a table to determine local minimum maximums and concave upward and concave downward. We're not actually going to sketch the graphs. We're just going to go through all the steps to gather all the information that we would need to sketch a graph. So let's start with our first one here. And we will start with the domain. So we're doing this function here. The domain, basically, we just have to make sure that we are avoiding taking the square root of negative, taking the logarithm of a negative or 0, and make sure that we're not dividing by 0. Those are the main 3 places we have to check. And in this case, we are in danger of potentially dividing by 0. X minus 1, x plus 1. This is the x squared minus 1 denominator. And set that equal to 0. And we can see that we have issues at -1 and at +1, meaning these values are not in the domain. So in interval notation, that would look like this. For the domain. Part 2, and I know they're all lowercase Roman numerals, but we're only doing this first function here for now, and then we will do the other one momentarily. Part 2, we want to find the vertical asymptote. We did vertical asymptotes a little while ago. That was in chapter 2, when we were learning limits and horizontal asymptotes. Basically, a vertical asymptote is going to be as the limit approaches a certain value, the y value shoots off to infinity, which means the limit doesn't exist. So basically what we want to do is our potential vertical asymptotes are at -1 or 1. So let's find the limit as x approaches -1 from the negative direction. It's going to be 2x squared over x squared minus 1. And one of the tricks that I showed you that we can do is go into our calculator and put the function in. 2x squared divided by, make sure you use parentheses, x squared minus 1. And then we can evaluate this. So numbers that are to the left of -1 are like -1.1 and things like that. So let's do y bars. And let's evaluate this at -1.01. Okay, let's get it even closer. 1.000001. And we're clearly going off to infinity here, to positive infinity. Let's do the limit as x approaches -1 from the positive side. That's -0.9999 and so on. So -0.9, we'll say. Looks like probably going off to negative infinity. Let's try it again. -0.99999. And we're definitely going off to negative infinity here. Let's take the limit as x approaches 1 from the negative direction. Or from the left side, I should say. So that's going to be a positive 0.9999. 0.999. And again, we're getting a negative infinity. And the last one, as x approaches 1 from the right side. So that'll be 1.00001 and so on. And we're definitely going off to positive infinity in that case. And this is very helpful for our graphs so that when we put our asymptotes in at -1 and 1, we know what's happening near those asymptotes. So we have vertical asymptotes at x equals 1 and x equals -1. And we even know the behaviors as we're approaching both of those vertical asymptotes. All right. Let's do part 3, which is a horizontal asymptote, which means I'm going to take the limit as x goes to infinity of the function. And we can actually apply L'Hopital's to this because this is infinity over infinity. That's going to be 4x over 2x, which it looks like this limit is going to 2. Because the x's reduce out, of course. And 4 over 2 is just 2. Let's see if we get a different horizontal asymptote if we go off into the negative infinity. We might. And once again, we have infinity over infinity once again, because we're squaring it, right? So it doesn't matter that they're negative. So applying L'Hopital's, negative infinity, we once again get 4x over 2x, which again is 2. So we have a horizontal asymptote at y equals 2. So again, what I did was we went off to infinity here. We got infinity over infinity, so I applied L'Hopital's and the x's reduce out. The exact same thing happens in the negative infinity direction. We do L'Hopital's, the x's reduce out. And so it's the same horizontal asymptote in both directions. All right, let's do now our, that was 3, so 4 is, the xy intercepts. So we'll start with the x-intercept, which is when y equals 0. So that's 2x squared over x squared minus 1 equals 0. Means 2x squared equals 0, which means x is going to equal 0. And when we plug in 0 here and here, we get the point 0, 0 is the x-intercept. For the y-intercept, that's when x equals 0. So this is f of 0. That once again is 0. So we have an x and y-intercept at the origin, which is obvious. But those are the only x and y-intercepts. All right, next up we have, let's partition this off a little bit. The critical values, which means I need the first derivative, which means we're going to be using quotient rule. So this is going to give me 4x times x squared minus 1 minus 2x times 2x squared over x squared minus 1 squared. And let's clean that up a little, because we're going to set that equal to 0. And it looks like we get 4x cubed completely reducing out. And by setting that equal to 0, the denominator goes away and we get, once again, x equals 0. This is our critical value, and our critical point is going to be the point 0, 0. I take that 0 and I plug it back into the original function. So we get a lot going on at the origin for this one here. All right. So next up, we have inflection values. All right, so now we need the second derivative. So I'm going to use this as my first derivative. So my second derivative is going to be the derivative of the numerator. It's negative 4 times x squared minus 1 squared minus negative 4x times the derivative of the denominator. This is going to be a little tight. This is 2 times x squared minus 1 times 2x all over x squared minus 1 to the 4th. And I'm going to factor out an x squared minus 1 from both of these. Actually, a negative 4 x squared minus 1 from both, and I'm going to be left with x squared minus 1 minus 4x squared. Yeah. Okay, so and that is all going to be over x squared minus 1 to the 4th, and I'm going to notice I can reduce one of these out. So we have negative 4, and in the parentheses, I'm going to end up with negative 3x squared minus 1 over x squared minus 1 to the 3rd. And I'm going to have to set this equal to 0. Divide the negative 4 out, that's easy. Add the 1, divide by negative 3, we end up with x squared equals negative 1/3. And that means we don't have one because we can't have a real number squared and have it equal a negative. So in this case, there are no inflection. There you have it. So let's work on the second one here. F of x equals x e to the x. All right. So let's start at the beginning. We'll start with the domain. Now, in this case, we have no limits. We're not dividing by 0 anywhere. We're not taking the square root of a negative anywhere. We're not potentially taking the logarithm of a non-positive number. So the domain in this case is very simple. This is just negative infinity to infinity, all real numbers. Next step, vertical asymptote. And again, we're not dividing by 0 anywhere, so there is none. Horizontal asymptote. So we do have a horizontal asymptote. Our y value, well, let's just take the limit. We'll start by going to negative infinity. Well, this is going to be going off to negative infinity, and that's going to be going off to 0. So now we have an infinity times 0 scenario. This is an indeterminate form of a limit. So we need to fix that so that we can apply L'Hopital's. So let's do this. So that's 1 over x. And now what we have is we have now as this goes to negative infinity, the whole thing goes to 0. And as this goes to infinity, that whole thing goes 0. So now I have the 0 over 0 scenario. So I can actually apply L'Hopital's. And I don't think this is going to make the situation any better. It's not. So let's try it instead of this way. Let's try it this way. Now we have an infinity over infinity situation. So when I apply L'Hopital's here, notice this just made it worse. So applying L'Hopital's here, I get 1 over negative e to the negative x, which is just e to the x, with a negative in front. And now as that goes to negative infinity, that is going to 0. So we have a horizontal asymptote at y equals 0. I could do it for the off to positive infinity, but the logic would be exactly the same. It would still go to 0. All right. Part 4. And we're looking for intercepts. Let's start with the x-intercept, which of course is where y equals 0. So we get x e to the x equals 0. Now, please note e to the x is always positive. This is always bigger than 0, which means the only way that this is strictly bigger than 0, so it'll never equal 0. So this will only equal 0 when x equals 0. So there is an x-intercept at the point 0, 0. Once again, that's not always the case. These two examples just happen to yield the same. The y-intercept is when x equals 0. So f of 0 is 0 times e to the 0, which is also 0, which we knew. Part 5. We need to find the critical values. So we're going to find f prime of x. So that's going to be 1 times e to the x plus x e to the x. It's pretty easy. And I'm going to rewrite this like this, because we need to set it equal to 0. And again, remember, e to the x is always positive, so I can divide it out. And I'm going to get this is going to equal 0 when x equals negative 1. So here is our critical value. So in fact, let's plug in, let's actually get a point so that we can do this. So f of negative 1 is going to be negative 1 times e to the negative 1. That's just e to the negative 1, or 1 over e. So at the point negative 1, 1 over e is our critical point. And well, we didn't explore the other one to see if we had local minimums or maximums or not, but we will with this one. I ran out of room. Let's do f double prime. We'll go back up here. And I'm going to be using this as my first derivative. So it's going to be product rule. So this is going to be e to the x times 1 plus x plus e to the x times 1, technically. And we want to set that equal to 0. I'm going to factor out an e to the x, and that's going to leave us with 1 plus x plus 1, or e to the x times 2 plus x. Set that equal to 0. And we will note, I can, once again, this is always positive, so I can divide it out. So we're going to have an inflection value at x equals negative 2. Let's see what that point will be. F of negative 2, I mean negative 2 times e to the negative 2, which is negative 2 over e. So our inflection point is the point negative 2 over e. All right, so let's explore local minimum or local maximum and so on. Let's do it for down here. So we only have 1, negative 1. And I'm going to be plugging this into here. So if I plug in negative 2, that's, again, this part's always positive. Negative 2 here is going to give me negative 2 plus 1 is negative 1. So that means over here, we have negative slopes. And then we can plug in 0 for this side. That's going to give us a positive 1 and a positive. So this is all positive here. Remember, when we go from a negative slope to a positive slope, we have a local minimum. At x equals negative 1, and the local minimum is (1 over e). Negative 1 over e. Negative 1 over e, pardon me. All right, let's do the same thing up here to see where we're concave up and concave down. Okay. So -2 is our only point of concern. And I'm going to be plugging my values into here. So let's pick -3. This part's always positive. -3 plus 2 is negative. This means negative. This means that we are concave down, meaning it's like this. And on this side, let's pick 0 again. So I plug in 0 there. That's going to be 2 times a positive value plus. So at -2, we change from concave downward to concave upward at the inflection point. All right. That is it for today. Thanks.